All right, welcome to class. So today we start the chapter on witness sets. This is arguably the main data type of numerical algebraic geometry. It is what allows us to handle solution sets which are positive dimensional. So we are today embarking beyond the problem of finding all isolated zeros of a polynomial system, which if you think about it, we haven't even done that yet. And we're going to talk about how to represent varieties of positive dimension. Now, I mentioned that we haven't really talked about how to find all isolated solutions to a polynomial system. So what do I mean by that? Where is the hole in our logic so far for us to be able to conclude that we can find all isolated solutions using homotopy continuation? I mean, can't I just cook up the Bézier homotopy, do a homotopy, and then, okay, modulo some numerical errors, as long as I keep these tolerances tight enough? I thought the whole point was that I get all the isolated solutions. So why am I saying that that's not what we've done yet? There's an important property of the polynomial systems we do know how to solve, which has been swept under the rug a little bit. And it has to do with the number of equations. Square, exactly. Yeah, so all of the polynomial systems so far have to be square. Okay. And that is going to actually show up as an issue really prominently in this section. So we're going to need to find a way to resolve this issue of requiring squareness. And that will definitely be part of the situation in this section. But before we acknowledge this and fix it, we are going to continue to ignore it, so I can give you the idea of what's going on. Because if I get into the theory right away, you might miss the forest from the trees. Okay, so. So what's the idea? The idea is somebody comes to you with some polynomial system like this. Okay. And they want to study this variety. Okay. But all you know how to do is find the isolated zeros to square polynomial systems. So the idea, and also parametrized square polynomial systems. And so the idea is going to be that we include sufficiently many hyperplanes in our equations. So if you had like an ax plus by plus c here, so that we do have a square system of equations. And then we find the isolated points of that. So a witness set for an irreducible variety come with an ambient space for free because we have coordinates and we have some number of variables. So we're in some Cn. So an irreducible variety. Let's say we already know its dimension for some reason. So of dimension m. Well, it's a triple. Call that a triple W. It's an F, L, and an S. F cuts out X as a reduced and irreducible component. L is a generic linear space of dimension n minus m. And S is a set of numerical approximations of points in X intersect L. And just one thing. Okay, so let's unpack this. So first of all, I'm only defining what a witness set is right now for an irreducible variety. We'll cook up a definition for witness sets for reducible varieties in a moment by just having witness sets for every irreducible component. All right, so we have an irreducible variety. Let's remind ourselves what an irreducible variety is. It's one that cannot be written as a reducible variety is one that can be written as a union in an irredundant way. Okay, what do I mean by irredundant way? I mean no cheat. Okay, so the empty set is a variety, so I don't want to write this parabola as the parabola union the empty set. That does not make it reducible. That is cheating. Points on this parabola are varieties. I do not want to write this parabola as the parabola union a point already on it. That is cheating. Okay, so irredundant, I mean each component of the union doesn't contain the other. Okay, so that's what an irreducible, and if you're not reducible, you're irreducible. Okay? So an irreducible variety, okay, dimension n. So our working definition of dimension right now of an irreducible variety is the length of a chain of subvarieties. So this parabola, let's call it X. X has inside of it a point. Okay, so this has two containment, sorry, yeah, no, it's not counting empty set. So this is a chain of non-empty, proper irreducible subvarieties. The point is contained in the curve. And so that chain has length 1, there's one subset, and so this is a curve of dimension, which is why we call it. Okay. Whereas, like, for example, if we had some surface, so that's my three-dimensional surface, we might have that is X, that is Y, that is Z, and yeah, indeed Z and Y, and X. And so this surface has dimension 2. Okay, now proving dimension this way is always a pain in the butt. Okay, because you'd have to consider all possible chains and show that you found one of maximal length. Okay. But that is the easiest definition of theoretically, right? The reason why these have to be irreducible, by the way, is call this one Z hat. Then I can definitely cheat like this, okay, and synthetically make this longer if I remove the requirement that they're irreducible. Okay, so that's why irreducible needs to be in there. Okay.
Say that again. Like, why?
So here, I found another chain of subvarieties. It's still a proper chain of subvarieties. None of these containments is an equality.
Yeah.
Okay. And if you think about it, I can make this as long as I like just by considering like 100 points on the curve, and then contained in that is 99 of those points contained, right? So if I remove irreducible in this definition, I'm not even gonna get something that's well defined because the maximum will not be attained. So we really need irreducible. So this is really a length 2 chain, and you can think about that as why this surface has dimension 2. All right. Okay, so we know what dimension is. Okay, so now we have the triple, which we're calling W, and that's FLS. Okay. So F is going to be a set of equations which cut out X. That's what you want it to be. You want it to be a set of equations which gives you X, and the number of equations corresponds to the dimension, right? So if I want to cut out a hypersurface, that's one equation. If I want to cut out something of one dimension smaller, I would take 2 equations, etc. And that would be your expected number of equations you would need to cut things out, but that's not always the case in algebraic geometry. So this is a non-trivial requirement right here. Okay, that the thing of dimension m is cut out by n minus m polynomials. Every time you intersect with a hypersurface, i.e. every time you include a polynomial into this polynomial system, you expect the dimension to drop by 1. Okay, so if I slice with n minus 1 hypersurfaces, I go from c to the n, and I drop n minus 1, which puts me in dimension n. Okay. And that's what you expect, and that's pretty much everything you've seen so far in this course. You're never going to accidentally write down a variety for which you can't do this. Okay, but some adversaries might be able to construct these, and we'll give an example today for you to hang your hat on when you think about situations where you can't cut out with the expected number of equations. Great, and so you'd really like X to just be V of F, right? But again, that's gonna pose problems because we have restrictions on the number of polynomials F can have. So by asking that X is just a component of V of F, we're actually giving ourselves a break. That means, okay, so maybe somebody has some variety, it can't be cut out by the right number of equations. But I can cut out a variety which contains it as a component, which is cut out by the right number of equations. Maybe enough alluding to this, and I give an example. Yeah. Okay. So the standard example is the so-called twisted cubic, and it's the image of this map. And if you take a different computational algebraic geometry class, you learn how to write down the equations for the image of this map. And the implicit equations are these. Okay. Well, let's give these names. This is a great counterexample to have in your back pocket. In fact, if you ever go to an algebraic geometry talk, this example will come up 80% of the time. Okay. Maybe a fact I haven't told you Parameterized varieties are irreducible. When you're parameterized by some c to the k. Which means the c is irreducible. And if you look at these equations, the thing you might be tempted to do. By the way, this has dimension 2 in C to the 4. Or if you like projective space, it's a curve in P3. Okay. But for now, this is dimension 2 in C4. And you're like, okay, so it's dimension 2. So I expect it to be actually cut out by 2 equations, right? The first equation will give me something of dimension 3 in C4. The second equation will give me something of dimension 2 in C4. So what's going on here, right? So if I think about each of these as hypersurfaces, v of f1, v of f2, v of f3. Okay, well, the first time I definitely cut out something, right? Because not every x, y, z, w satisfies this equation. So I'm definitely a hypersurface here after cutting it. Okay. And this is an irreducible polynomial, so I am an irreducible hypersurface. So I slice again. And indeed, not everything that satisfies this will satisfy this. And you can, I mean, if you just pick a random x, y, z, w that satisfies this, and check it against this, you'll see that pretty fast. And so I'm cutting out something more there. Okay, so already when I include 2 equations, I'm definitely in dimension 2. Okay. So why not just consider this? Or any of these, right? So this C lives in each of these varieties, because each of these varieties just removes an obstacle to being able to belong to C. Okay. But none of these varieties are C. Each of these has an extra component. Okay. So for example, if I want f1 and f2 to vanish, there's a cheaty thing I can do. So this is actually equal to, it's C union a particular plane where Z is 0 and W is 0. Let's convince ourselves of that. Okay, so I definitely know C is contained in here. So why is this contained in here too? Well, if Z is 0 and W is 0, this vanishes. And if Z is 0 and W is 0, this vanishes. Okay. So yeah, definitely that's in there too. And that's the same for all of these, albeit it's a different combination. So if I want F1 and F3 to go away, Z and Y will do the trick. And if I want F2 and F3 to go away, Y sticks in. Okay. And pretty much no matter what you try to do, you are going to pick up this extra 2-dimensional linear space. And that's a feature of these equations. So we don't know how to handle this situation yet. Okay. But what's written on the board is alluding to how to handle this. Okay, we can't replace the equations cutting out C with equations that cut out C but have the expected number of polynomials in it. But we can replace it with something that has the expected number of polynomials, which cuts out C as a component. And that'll end up being the trick that we do. Okay, back to the definition of a witness set. All right, so witness set is a triple, a bunch of polynomials which cut out the variety I care about as a component. Okay, so that's actually relaxing our situation that we have. Okay, I want it to be irreducible. We've talked about what that means. Have we talked about what it means to be reduced with respect to a set of equations? Okay. Reduced means Alex didn't come and screw up the equations to confuse us. That's what reduced means. Reduced means you're hanging out with your friends and not your adversaries. And so let me give you a proper definition here. So this and it might be just a reminder. First thing we need is that X is indeed a component. Okay, so if you're some union of 5 varieties, if you want to be a reduced component, you better first be a component. Second, the rank of the Jacobian of X evaluated at X is equal to the codimension X for a generic. Not being, in other words, not being reduced is exactly the obstruction to defining dimension with respect to the rank of a Jacobian. So we want X to be reduced and irreducible component. We want L to be a generic linear space of dimension n minus m. Which, by the way, this is equal to the so-called codimension of X. All right, so if you have something of dimension m inside of something dimension n, its codimension is n minus m. Sometimes called the complementary dimension. Now, what do I mean by generic? We've seen this pop up before. And we do have a definition. How does it apply here? Non-singular. I need the L to be non-singular? Oh, I was thinking the X. Over X and X. No, this is not going to be saying something about how singular X is. Let me give you an example. This is also a linear space, complementary dimensions with parabola, but it is not generic. Now, when people say generic, they mean one of two things, and one subsumes the other. So generic in general means outside of a Zariski closed set, proper Zariski closed set. So it means outside of some variety. And since varieties are proper subvarieties that are small, it pretty much means the same thing as a random one will have this property. Okay. So for all intents and purposes, L being a generic linear space means just pick a random one. Pick a random one, you'll be fine. Okay. But sometimes when people say generic, they don't just mean that it's outside of some variety. They can actually identify what that variety is. Right? And that's like extra special. Okay. We're not going to do that. But instead, I have to convince you probably this. The world of linear spaces of this dimension is itself a variety. So I could talk about some varieties of it. Does that make sense? The usual space in which we've seen generic so far is in the context of these like parametrized polynomial systems or these branch covers, where we have some pi down to some c to the k. And I'm talking about generic with respect to this parameter space. But that's not too hard for us because we're like, oh, okay, subvariety of c to the k. I know what a subvariety of c to the k is. So I know what it means to be outside of one. So generic makes sense there. But now what I'm saying is generic as amongst all linear spaces of a particular dimension. Okay. Thinking about this one. Now, people think about this space a lot in math. And if you plan to continue your world of algebraic geometry, you would call this GRK plus 1 n plus 1. That's called the Grassmannian of k plus 1 planes inside an n plus 1 space. Okay. So I've added a plus 1, I've added an affine here. In linear algebra, you learn that all vector spaces contain the origin. And all vector spaces look like linear spaces. In algebraic geometry, the origin kind of doesn't really matter. You're allowed to translate that line around. This is linear space of dimension 1. Right? Even though it doesn't go through the origin. Right? So I don't want to look at all vector spaces of dimension 1 inside a two-dimensional vector space. What I really secretly want to do is look at vector spaces of dimension 2 inside a three-dimensional vector space here. But if you don't like that language, that's totally okay. You should really think about this as I want it to be dimension things. You don't like Grassmannians, that's fine. You do know that all such linear spaces are the solution sets to equations that look like this from linear algebra. Where this is a k by n full rank matrix. This is an n-dimensional vector. Okay. All affine linear spaces are solution sets to this. And as long as A has rank k, this solution set represents, sorry, n minus k. So as long as A has full rank n minus k, then the rank nullity theorem says that the solution set has dimension k. But then translated by something, because it's not homogeneous. Oh. So you can just think about this as your space of k planes in n-dimensional space. Okay, so it still looks like essentially an open subset of like a big C to the something, right? What's the condition? The condition is that this needs to be full rank. But that's cut off by polynomial equations. If you just randomly fill up a matrix with numbers, you'll be full rank. Okay. So that's what generic means. And you can engage with that either on the level of Grassmannians, on the level of this linear algebra, or just on the level of replace generic with random and don't press too hard about it. Okay, so far, what is a witness set? A witness set is a triple, including equations which cut the variety you care about out in a not weird way. A linear space of some appropriate dimension, randomly chosen. And S, a collection of numerical approximations for the finitely many points in this intersection. So this red line is my L. Numerical approximations for these 2 points, so maybe it's like really close, but not quite. Comprise my S. Any questions?
That will be n minus k, right?
Sorry?
C raised to n minus k.
This is
This
n
is-
minus k times k cross n.
Is it n?
So yeah, so I need to pick an n minus k by n matrix
Yeah,
and a vector.
n minus k by n.
N minus k, yes, thank you. Yes, absolutely. Oops. Thank you. Yeah. Oh, great, sorry. Oh no, whatever. It's some big C to the n, but thanks for catching that. That's okay. Okay. So let's think about the problem of hooking up a witness set for this parabola. This is a parametrized polynomial system. I've written it as such. Upstairs, we have a set of all x's, let's say, just do an ABC. X. Oh yeah, I guess that's more annoying. Bring to the Y here. Yeah. So that's the incidence variety of the parametrized polynomial system. Goes out of the parameter space. The parameter space is lines in the plane. And if we throw coordinates on it like this, okay, this space is not the space of lines in the plane, but it pretty much is. For example, if A, B, and C are all 0, that's not a line in the plane. Okay. So if somebody's being technical, no, this is not the space of lines. But as long as everybody's chill, then yeah, this is the space of lines. This is how you do it on a computer. And so if I pick a point here, which remember, I think of, where's my red? That's some line. Then above it will be 2 points. which I think of as the intersection points of that line with the variety I care about. Okay. And we saw this before. This is called the witness parameterized polynomial system. And so when you have a parameterized polynomial system, one of the first things you're going to do, sorry, when you have a setup like this, some incidence, the first thing you're going to try to do from a computational point of view is to find equations. Right, so if somebody just hands you some x, say the twisted cubic, you want to get equations for this. But you want to get equations which satisfy the parameter continuation theorem so that you can do all this parameter homotopy stuff. Which means I can't use the 3 equations which cut out the twisted cubic. Right? I need to reduce my number of equations. And the cost, the price I pay for that is I might pick up extra components. Okay. And that means that when you cook up this witness parameterized polynomial system, you're going to have to make a choice to reduce the number of equations. And then even after you do that, this might not be irreducible. It might be reducible, where components correspond to components of x. And so we'll have that technically laid out in the subsequent lectures. And that is why we introduced this notion of reducible branch covers. So recall. Branch cover is a map, a dominant map of irreducible varieties of the same dimension. Irreducible is one where you just have lots of components. Okay.
Dominant.
Say again?
What is the definition of dominant map again?
Essentially surjective. Surjective in the algebraic geometry sense. Means the risky closure of the image is the whole space. Yep. Equivalently to being a dominant map here. You can ask for it to be generically defined. Yeah, that's going to be this.
Okay, very good.
That'll be this. In general, you expect the dimension of the thing upstairs to be the dimension of the thing downstairs plus the dimension of the generic. But you need irreducibility in all of this. Good. Okay. I'm going to erase this bad line. Bad. And so F could be this, but F could also be this. Okay, so now the first polynomial is a product of two. Okay, and yeah, indeed I have some. That's a circle centered there. And I might have, okay, so now X here is parabola union circle. And so now when I slice, I get 4 points. But I have my F. Maybe I should. That's not part of my F. That's my F. Okay. So F needs to be a set of expected number of polynomials to cut out the parabola. I expect one polynomial to cut out the parabola. Indeed, this is one polynomial cutting out the parabola, which is the product of two. It's kind of a cheater's way to do it.
And the slice is the red line.
Yeah, exactly. Yeah, I just drew a random red line. Or if you'd like, you include linear forms with random coefficients. And that is the same thing as choosing an A and a B so that AX equals B. Awesome. So what I'm telling you is that a witness set for the parabola is W F at L S1 S2. Call that F W. That's a witness set. This is a witness set for the circle. It's really important to see what's going on the parametrized polynomial system story. So for this example, I still want this to be like our V of F. And this is still going to be some random parameterized polynomial system. You could write this down, do it. And a generic fiber of this map has how many points? 4. 4. And what do you think the monogram here is? Yeah. So Deepak says he thinks it's S2 cross S2. Trick question, didn't define monodromy group for reducible branched covers. But indeed, you can label these points in some chosen fiber. You can do loops around. And indeed, you'll get some permutations. So upstairs, we have 1, 2, 3, 4. And these two are on the parabola, and these two are on the circle. Then as we move around by taking this linear space and moving it around the plane, the points that are on the parabola have to stay on the parabola. The points that are on the circle have to stay on the circle. Why? Well, how would you go from the parabola to the circle? You would have to cross the intersection of the parabola and the circle. Right, if I'm going to continuously move as a point on the parabola to the point on the circle, it may seem plausible that I can move down and over, right? Okay. That would require me to be a point on the intersection at some point. But points on the intersection are in the ramification locus of this map. The Jacobian's dropping rank. Okay, so these are exactly the points we're taking out because you can't do home continuation. And this consequence has huge implications. Sorry, this result has huge consequences, i.e. implications. it means that if I cook up this witness set, so I'm only writing down these points. Sure, I can solve the whole thing. I'm going to throw away the ones that are on the circle. Okay, so now I got this triple in Julia. F is my equations. L is extra equations, which are parameterized to give me linear spaces. And I have a couple of numerical approximations of points, which are solutions. As I move around, I am always going to be a witness set for the parabola. Right? That would fail if S1 jumped onto the circle. Like if S1 and S4 swapped, then as I moved around continuously in this parametrized polynomial system, I would lose this property of being a witness set for the parabola. Eventually. Unless I had some result saying the points on the parabola need to stay on the parabola as the linear space moves. Right. Questions? Somebody hands you a variety. You want to represent it in numerical algebraic geometry world. The first thing you do is you find a set of equations which have the expected number of polynomials and cuts out that variety as a component. Don't worry if you cut out extra components like we did with the twisted cubic case. That's fine. It's not going to be an issue. We're just going to ignore points on those components. Don't worry about it. Okay, now we include parametrized polynomials describing a linear space. And because we have the expected number here, and the linear space has complementary dimension, I will now have a parametrized polynomial system, which is squared. And that is what we can do parameter continuation over. And that is what we get the parameter continuation theorem for. And that means that if I have a witness set, I do not just have some nice equations of linear space and points. I have all of that, plus I have the power to move those points continuously as the linear space moves around. That will not seem like a very powerful superpower to begin with, but it's incredibly powerful. Let me give you one example. So now I'm going to give you an algorithm to do something that you do care about. And it may or may not surprise you that as soon as you have witness sets, you're good to go. So 1. Two will be a witness set x2 in the same space. Okay, so they're both irreducible numbers. One thing you might want to know is whether or not these two varieties are the same variety. Okay. Or whether or not one variety is contained in another. If you've taken any symbolic computation, you know this is essentially the fundamental thing that like Grosvenor bases are doing for you. They're giving you ideal containment, which on the geometric side is telling you something about variety containment. And I think here it's really, really easy. Okay. What's the algorithm? Okay, so this is my L1 now. So don't care about these. This is a witness set for the parabola. That's a witness set for the parabola. L1. L2. So witness set. Oops. For this poorly drawn circle.
Instead of S4, should you have kept S3?
Yeah. Yeah. Thank you. Call it a test. Call this S3 and this S1. Okay, everything's on the right place. And let's just make it really clear. You're a point, you're a point, you're a point, you're a point. Okay. The only way the parabola here will be equal to the circle is if a random point on the parabola is also on the circle. Right, so if two varieties are different, you can tell that by just choosing a random point on one of the varieties and asking if it's on the other. So what's the algorithm to do this? Just move L1 to L2. Okay, so move L1 over to L2, do the tracking, and this point will go there. This point will go there. And since these 2 points is not the same thing as these 2 points, they're different varieties. If they were the same variety, they'd be the same point. Wow, so immediately from the definition of a witness set, you get variety, irreducible variety equality.
Should this be S1 and S3 or is it?
Capital.
Oh, okay.
Yeah.
Oh, I see.
So, okay. So yeah, so here this is gonna be capital S2, capital S2. Yeah, so that's general, right? So I'm assuming, I guess I'm. I'm just saying I have this data type, right? But remember, I don't just have this data type. With holotopic continuation, I have the ability to move it around, right? Which is what I need to be able to do this. And that ability is super, super, super strong. You will be able to talk about variety of payment, whether or not something's an irreducible component of another thing, how to find the irreducible components of a variety. You will be able to trivially write down witness sets for images of varieties. Right, so if you studied symbolic computation, you know, doing, finding the implicit equations, right, for the image of a map is really, really, really hard. That requires some sort of elimination. Okay, but here elimination is going to be trivial. Okay, so this data type is really containing a lot of geometric information, and therefore it plays really nice with geometric operations. Whereas in the symbolic case, you have defining equations for an ideal, and elimination is a super hard thing to do. Because elimination is really inherently a geometric operation. That's the class. Sorry for going 3 minutes over. I'll take questions.